Okay, I think we are live. I think we are live. Let me quickly check my sound. Okay, I think I'm audible as well. So, in case if you face any problems, if you think that I'm not audible or something, just let me know in the chat quickly, or otherwise we can start. Okay, so we'll be solving the problem of the day for yesterday. So it was basically you have to do insertion sort for a single linked list. So insertion sort is a sorting technique that will basically sort a array or a linked list that you have. So the output should be the sorted linked list, obviously. And you have to do insertion sort, although there's no way to verify what type of algorithm you're using. But again, like when it comes to an interview, the interviewer will actually look into your code, so definitely he'll understand that you are using a different approach. So yes, you have to do insertion sort. So we'll try to do that only. And yeah, given a single linked list, you have to sort the list in ascending order using insertion sort algorithm. So you are given this linked list here, so it's 30, 23, something like this, and the output is now in sorted fashion. So 11 is the lowest, so it comes first. After that 14 is here, after that 16, 19. So if you see, the output is in a sorted fashion, right? So the question is pretty simple. There's nothing to explain. You have to sort a linked list, and the algorithm that you have to use is insertion sort. So I think there should not be any problem with respect to the question, at least. So we'll jump into the solution, like how do we solve this. And first of all, can anyone tell how does a insertion sort algorithm work? So let's say you have let's assume any data structure, array or linked list. We don't care for now. We just want to know how insertion sort algorithm works, right? So after that we'll design it specific for a linked list. How do we do that? But for now, let's just assume that we want to understand how insertion sort works. So we'll take any random array, let's say 13, 10, 11, 3, 7, 14, 2, something like this, right? Let's say we have something like this, and we want to do insertion sort, right? So this is the array, and we want to do insertion sort on this. So how do we do this? Insertion sort is like, what you have to do is, for every iter swap happens, yes. So what we do is, it's kind of, you can think about insertion sort to be something like elements are coming in. Just you have a dynamic array, right? You have a dynamic array, a element is coming in every time, and you have to insert that element in its actual position. So that's basically insertion sort algorithm. Like that's exactly how it works as well. Although we don't have a dynamic array, but we'll treat as if the elements, like initially we'll start off at 10, so we'll assume that only 13 and 10 are there, the remaining are not there. We'll insert 10 in its actual position in 13, 10. After that, we'll assume that dynamically 11 is coming, so we have to place 11 in its actual position. After that, 3 is coming, and we have to place 3 in its actual position. So that is the algorithm of insertion sort. So let's actually quickly understand that how it works. So first of all, we have 10. We have 10 here, right? So we start off at the second element. There's no point of starting at the first element. We'll start off at the second element, 10. So we'll check with the previous element. Is 13 greater than 10? 13 is, yes, it is greater than 10. So 10 should come before 13, right? So we will not swap right now, but what we'll do is we'll keep the 13 here. We'll just change the position of 13 so that we can create a space for 10 to come. But we'll not place 10 here yet, because we are not sure if this is the place. We'll directly place 10 in its actual position, and we are not sure yet that this is the actual position where 10 should be. So now we come to this point. So we'll come to this point, yes. So is we see that there is no more elements left, so this is the only point remaining, so we can now safely place 10 here, right? So this is what happens in the first iteration. Now let's go to the second iteration. So in the second iteration, we come here. So whenever we come at 11, and we start from the previous element, 13. So is 13 greater than 11? Yes, 13 is greater than 11, right? So we will place 13 in the place of 11. We'll place 13 in the place of 11. Now 11 will not place here until we are sure that this is the insertion point of 11. So we'll move to the previous step, that is 10. Is 10 greater than 11? Is 10 greater than 11? 10 is not greater than 11. So this is the insertion point of 11. We'll place 11 here now. Okay, so this is how we place 11. Now we'll move to the next step. So we have 3, right? We have 3. We start off here. So let's write 3 here. Let's just remove 3 directly from here. So 13 is greater than 3. It is. So we'll move 13 here, right? Now we will not immediately swap. We'll come to 11. Is 11 greater than 13? Yes. So we'll move 11 to the next position, creating a space for 3 to come in. Now we'll not place 3 here yet. We'll again go back one step. Is 10 greater than 3? Yes, it is. So we'll again move 10 by one place. We'll move 10 by one place, and finally we have position for 3. We have a space for 3, so we can place 3 here now safely. We are placing here 3 here safely. Now note that the way we are moving these elements, right? We are moving the elements to the right. That is to create space for 3 to come in. That's why we are moving the elements to the right by one place. So we have sorted up to this position. Now let's go to the next one. So we'll go to 7. We'll go to 7. So the element under consideration is 7. Let's remove it here directly. So 13 is greater than 7. Yes. So 13 comes to this position. 13 comes to this position. Now we'll go to the previous step. 11 is greater than 7. Yes. So 11 moves to the next position. So 11 comes here. After that we go to 10. 10 is greater than 7. Yes, it is true. So 10 is moved. And finally we go to 3. Is 3 greater than 7? No. So we know the insertion point of 7 is the next position of 3. That is this. So 7 is inserted here. And we'll move to the next position. So we have 14. Okay, so we'll write 14 here. We'll immediately remove 14. Now is 13 greater than 14? No. So we know that the insertion point of 14 is wherever it was. So we will again insert it back here and we'll continue. So 2. Now 2 will immediately remove 2. So let's remove 2 quickly. So 2 comes here. Now 14 is greater than 2. Yes. So 14 is moved. 14 is moved. So 14 will move it by one place. 13 is greater than 2. Yes. So 13 will be moved. 11 is greater than 2. Yes. So 11 will be moved. So we are moving backwards, right? 10 is greater than 2. Yes. So 10 will be moved. 7 is greater than 2. Yes. So 7 will be moved. 3 is greater than 2. Yes. So 3 will be moved. And finally we come to the end. So 2 should be placed here. So 2 is placed here. And if you see that after this, we have the entire array sorted, right? We have the entire array sorted. So basically the steps of insertion sort, like what you should do is you should find insertion point of the given element, find insertion point of the incoming element, where this incoming element should be inserted if the array has to be kept sorted. So find insertion point of the incoming element and insert into that point. Insert into that point, right? So this is the algorithm for insertion sort. You'll assume that the elements are incoming, so you have to find the insertion point of the incoming element. That is, given this element is coming, where should you keep it so that the array that you have formed till now, it is sorted, right? So that's what we are doing, and then we are inserting into that position so that it is sorted, and we are going to the next element. So this is the insertion sort algorithm. Any confusion with this? Like, how is this working? Can you guys quickly let me know in the chat if you have any confusion with how insertion sort is working? Is it clear with everyone how insertion sort works? So that is how I remembered. I remember it like this, that means it is very easy to be confused between selection sort, insertion sort, bubble sort, right? But how I remembered is, I generally remember like this, that insertion sort is kind of for a dynamic array. So one of the elements will be coming every time, and you have to find the perfect insertion point for that, for the array that you have sorted till now. Into that, where should you insert? Once you find that, you have to insert at that point. So that is how I remember generally, right? And that's the idea of insertion sort. So is it clear with everyone how insertion sort works? After this, we'll learn how to actually do insertion sort on the linked list. So let me know in the chat. Please write yes if you have understood how insertion sort is working. Please write yes. And if you haven't, let me know. I'll explain again. Please write yes if you have understood. Okay, great. So let's move ahead. So let's understand how would we do this for a linked list, right? So for a linked list, what we'll do, let's see, let's create a linked list, right? Let's create a linked list. 7, 3, 5, 8, 4, 1, 2, something like this, right? Let's say we have a linked list like this. We have to do insertion sort. So we'll use a similar approach, very similar approach, but here we'll not actually move the element to the right by one place or something like that. Because why did we move the element to right by one place? Just think about this. Why did we move each element to the right by one place when it was greater? It is because we were creating a space for the incoming element, right? But here we don't need to create a space, right? We have the flexibility of having a linked list. We have that flexibility that we have a linked list, so we can, in a linked list, it is very easy to insert an element in between two elements. Like if you have two elements, you can easily insert an element in between two elements, right? Or two nodes. It is very simple with a linked list, so we don't actually have to move everything by one place. So what we'll do, this is the head, right? This is the head. So we'll start off at 3. We'll start off at 3. So this is where we are at. Now we'll compare with the previous. So we'll start off always. There's no way of going back, right? In a linked list, in a single linked list, we cannot go back. So we will move from forward and find what is the insertion point. That is what is important, right? It doesn't matter if we are moving backward or we are moving forward. We just have to find what is the insertion point and we have to insert into that point, right? So we'll try to determine the insertion point. So we'll start from the head again. So we see that 7 and we have only one element 7, and that is the insertion point. So basically 3 should come before 7. So we can easily do that. How do we do that? We'll basically make the next of 3 point to 7. Next of 3 will point to 7, and next of 7 will point to 3's next, that is 5. So we can easily do that. So how it changes basically after one iteration is 3, 7, 5. 3, 7 and 5. Now we are at 5. We have to find the insertion point, right? So we again start from the start. 3 is less than 5, so this is not the insertion point. So we'll move to the next point. 7, this is the insertion point. 7 is the insertion point, right? So we will also keep a pointer to the previous element, that is 3, right? So that if you see, the next of 3 should become 5. So that's why we need a pointer to the previous element as well, and we can easily do that. We can easily maintain a pointer to the previous element. So we have a pointer to 3, we have a pointer to 7, and this is the insertion point. So basically next of 3 will be 5, next of 3 will be made 5, next of 7 will be made 8, and next of 5 will become 7, right? So it basically becomes this is broken and this is gone, so it becomes like this, right? So basically what happens here, 3, 5, 7, like this. 3, after that 5 is coming in, 3, after that 5 is coming in, after that 7 is coming in, and after that 8 is coming in, right? So now we move at 8, we come at 8. Now for 8 we have to find the insertion point, right? So we start off at again at 3. We have two pointers, previous and next. So 3 will be moved. So 5 is also less than 8, so again it will be moved, and previous is also moved to the previous point, right? Previous is also needed, so previous will also be moved with this. So previous is moved to 5 now. 7 is greater than 8, 7 is also less than 8, so it is moved again. But we see that we have come back to 8, right? We have come back to 8. So 8 is already in its position. 8 is already in its position. So we don't have to do anything. So we'll again move to the next element, that is 4. So we'll move to 4. Actually, let's take a different color for the 2 pointers, right? So initially both the pointers, the current and the previous pointers will be at 3. So 3 is less than 4. So the next pointer will be moved by 1 place. The next pointer will be moved by 1 place. So it will be moved to 5. 5 is greater than 4. Now the previous is at 3, the next is at 5, right? The next is at 5. So 3 is next will be 4. The previous is next. That is 3 is next will be made 4. This will become 4. The next of 5 will become the next of 4, that is 1. And 4's next will become 5, right? 4's next will become 5. So basically what happens here is this is broken. This is broken. Okay. 5's next is 7, 8. Okay, now no. This is actually interesting. Now we cannot what was there? We had, what did we have here? We had a 4 here, right? Okay, we had 4 here. 4 is pointing to 1. Now 5's next, if 5's next points to 1, actually this 7 and 8 will be broken, right? This 7 and 8 will be broken, although it's in a sorted fashion. So what we should do is we should also maintain a tail, like it should come after 8. It should come after 8. 1 and 2, right? It should always come after 8. So what we'll do here is we'll make the next of 3, that is we'll make the next of 3 to be 4. So 3's next becomes 4. Let's write it down here. 4's next becomes 5. And we are making, instead of making 5's next 8, we'll make the last elements next 8. So sorry, 1. So 8's next will become 1. Otherwise, if I make 5's next 1, then 7 and 8 will be broken. All the 7 and 8 we have already sorted, right? We have already sorted 7 and 8. 1, 2 we haven't yet sorted. So that's why we don't want to break this link, right? We don't want to break this link. So we'll make the last element point to this. Now we'll move to the next element. And it makes sense, right? It makes sense as well. So we'll move to the next element, and again we'll do the same thing as again, right? We'll repeat the same thing. The next of 8 will become 2, and 1, as it is the smallest element, it will come to the front, and the next of 1 will become 3. So this will happen after this iteration. So next of 8 becomes 2. So this is how this entire thing will work. So let's quickly write down the code for this and see how can we do that. Okay, so let's see. We have the linked list given to us. Right, we have the linked list given to us. So what we'll do, so node, what are the things that are needed? One of the thing that is needed is the current node that will be sorting. So that is equals to head initially, head ref, current node that will be sorting. We have to write a struct. Okay, struct node current head, current equals to head ref. We also need a few things like what do we need? Actually we can actually give up on actually combining 8 and that, right? Like even if we don't combine, I'm just thinking about this, that even if we don't combine this, right, we can just, even if we don't combine this thing 8 and 2, right, it doesn't matter. Like we just, it is wrong actually to combine 8 and 2. So we'll not combine only, we'll just maintain a pointer to this. Anyways, after 2, whatever comes in, we have that using this pointer. We'll always have that. So there's no point in combining 8 and 2, right? We can combine, but there's no point in combining. We'll never actually access this point. And anyways, it is wrong to actually combine 8 and 2. So that's why we can just maintain this thing separate. Like we can just maintain this thing separately without combining. So that we can do. We don't actually need the previous link there. So that's what we'll do. So we'll maintain this, and we have the head ref definitely. So okay, so let's do that. So current is head ref dot next. So we'll directly start from head ref of next, right? So if current equals to null, we'll directly return head ref, right? We'll directly return head ref. Otherwise what we'll do, what we'll do is we'll make something. So node current equals to headref of next. Now what we'll do, we'll find the insertion point of current, right? So node star struct node star, we are finding the insertion point. So struct node star first, like previous and next. So we are finding the insertion. So let's call it current inserted inserted element, right? Something like this, inserted element. So that is basically this thing. So inserted element equals to null. So if inserted, like there is only one element basically. If inserted element is equals to null, then we can return headref. Otherwise, what we'll do, inserted element, we have current and we have previous. So we'll maintain these two things. Now, first thing that we'll check here is if what if the element at the root is itself smaller than the is greater than the given element. So that is headref. If the element at the root headref of data, if it is itself greater than the current element, that is current of data, right? Let's not give spaces here. So headref of data is current of data. In that case, what can we do? If headref of data is greater than current of data, that means the new element will come at the head. So before that, we'll make one thing. So node struct node star next, struct node star next equals to current of next. Now current of next will point to whatever headref points to, right? Because that will, like, just assume we have at head we have 2 and the current element is 1. So 1 is coming before 2, right? So the next of 1 should become 2. So headref and headref equals to current. Headref equals to current. Okay, headref equals to current. So this is the element that we are inserting, in its place. Other than that, what will we do? That's fine. I think that's fine. Else, if that is not there, so we'll move while. Sorry, it will. I think it will not be current. It will be inserted element, right? Inserted element. Inserted element. Here also it will be inserted element. And here also it will be inserted element. The name is a bit confusing. I don't know what can be a good name to give this. So inserted element, right? So while otherwise what we'll do, we'll start off at current and head to be current equals to what? Current equals to headref and headref next, and previous equals to headref, while current of data is less than equal to or less than is fine. Current of data is less than inserted element data. So as long as it is less than inserted element data, we'll do is previous equals to current equals to current next. We'll move like this. Okay, as long as we don't find the actual insertion point. So yes, current dot data. Also, one more thing we can do is and current not equals to inserted element as well. We can do this as well as and current, although it will be, if it is equals to inserted element, then less than condition will be anyways false, right? The less than condition will anyways be false, so we don't actually have to do that. Okay, now what we'll do is, okay, so we'll have the next. So struct node star next equals to current equals to who's next? The inserted elements next. So insert elements, it's next. Now current is the actual insertion point, right? So previous of next will be equals to what? Previous of next will be equals to current. Previous of next will be equals to current. Also one more thing, if I'm inserting one element, let's say I'm inserting this comes first. So so if this happens, next, so I'm assuming always that the last element is null. We have to maybe do somewhere, we have to check care of null somewhere, right? So inserted element of next will be null, will be equals to inserted element next. Previous of next will be equals to current, not current, it will be equals to inserted element. And inserted element of next will be equals to current, and we'll be doing this, and current equals to, okay, current equals and sorry, and what, and inserted element, and in both the cases, actually both the cases, inserted element should be increased. So inserted element equals to inserted element of next, right? And while inserted element this, and the null headref, and here we'll do while inserted element not equals to null. So this will continue basically while inserted element is not equals to null. This entire logic will continue, but again we haven't actually created the null condition anywhere, so we have to take care of the null check actually. When can we set it to null? That's something that we have to understand. So while this yes, so let me write it down properly. Now I think it looks good. Okay, so when will we make it null? When will we make this null? That's interesting. What if whenever we are going for an inserted element, we should make sure that, okay, for when this happens, right, when this happens, it's going to the front, and we are assuming that every time it is actually broken. So whenever we are going to the next element, what we can do is we can break the, if there is any previous connection, we can just break that. So this will also point to this. Okay, so we have to maintain a previous connection for inserted element as well. So inserted element equals to null. So inserted element is that, and struct node star prev to inserted, previous to inserted equals to head, and prev to inserted, its next will become null, and prev to inserted, its next will become null, and inserted element is inserted element next. All the inserted element is not inserted elements next, because inserted elements next is current, and we are storing it in next. So here we should do, here we should actually do that, right? Head ref equals to inserted element, and where are we storing? Inserted element of next equals to head ref, and here actually inserted element equals to, so we can actually take this out completely, right? We can take this out completely. I think this is not needed anywhere, so we can just take this out completely. So let's take this out completely from here, and this is also then this is also coming under the same thing, while inserted element if and else. Okay, so this is also not needed here, and next is that. So inserted element will be equals to next, inserted element will be equals to next. inserted element will be equals to next, the next that we have taken out, right? And previous to this should be that, and finally we can return, I think we are safe to return headref. We can try dry running this before submitting, but anyways, let's see if the code is compiling. There might be some issues I'm not sure about. So this compilation issue, previous to head, head was not declared in this scope. Okay, that was head ref, I believe. Yes, that is head ref, and I think that should be okay. So let's see. Okay, 30 I think. Okay, I think it's working, so let's submit. And it's not working here, it is giving a segmentation fault. So let's see why is it giving a segmentation fault. So it's 18 30 23. It's pretty simple input that is given to us. So 18 30 23, let's see. 18 30 23. I'm pretty sure that there is some mistake with respect to the null assertion or something, null assignment. So first of all, inserted element, we are starting off at dot next, right? So we are starting off at inserted element at this point, and it is not equals to null, so definitely it will go inside this while loop. It is not equals to null, yes. So what we'll do here is we'll take the next to be equals to inserted elements next, right? So the next will basically point to this 23, the next will point to this 23. That's fine. Now head ref of data, if the head ref of data, the head is still at 18, right? So if 18 is head ref of data is greater than inserted element data, if 18 is greater than 30, which is false, right? Which is false. So we'll go to the else statement. Current equals to head ref dot next. Current equals to head ref dot next, that is current will start from here, and previous equals to head ref, I believe previous is equals to head ref, so previous will be here. So current equals to head ref dot next, previous equals to head ref. So while current of data is less than inserted element of data, so what is current of data here? Current of data is 30, inserted element of data is 30. Is 30 less than 30? No, right? 30 is equals to 30, so will not get into this loop. After this, what we'll do, previous of next equals to inserted element. One second, previous of next equals to inserted element. So previous of next, what is previous? Previous is 18, 18's next equals to inserted element, which is 30, inserted element of next will be equals to current. Current is itself equals to inserted element. So here we should add another condition here, that if what, if current equals to inserted element, then we should not do this. So not equals to, then we should not have this condition. Sorry, yes, we should not have this condition, right? Otherwise we can have. So now previous of to inserted, what is previous to inserted of next? Previous to inserted is, the inserted element is 30, previous to inserted should be 18. 18's next will be equals to null, which is wrong again, I believe, which is wrong again for this case. So we should not, this one should be here only. If this is true, then only we should do previous to inserted equals to null. And let's see, we'll see that also. And inserted element equals to next, inserted element equals to next, which is okay. So inserted element equals to next. So where does inserted element go? So inserted element will go to the next, that is 23. So it will just go to 23, it will remain the same, it will just go to 23. And in this case actually we can do 30's next can be set to null. So 30's next actually can be set to null, but again it will be, I think, set to null in the next step only. Like here only we'll set this to null. Here only we'll go to 30 and we'll set the next of 30 to null actually. Let's see. Yes, I think we should do that. So 30 is next. We can just set this to we'll anyways set this to null, because in the next step 23's insertion point will be this 30. 23's insertion point will be 30. So we will, what we'll do here, 20's insertion point will be 30, so we'll come into this condition, I believe. The first condition will not be true, the second condition will come to that. So current of data is less than inserted element of data. This is outside else. Okay, right. So current of data is less than inserted element of data. In this case also we should actually do previous to inserted. So let's do in this case as well. So if previous to inserted not equals to null, previous to inserted equals to null, previous to inserted of next is equals to null. I think this will be null after the first iteration only, and we don't have to. And here also, if previous to inserted, if previous to inserted not equals to null, and after that we can set it to null. So after the first step only it will become null, and after that it will remain null. We don't have to take care of this. Equals to null, and the next will also be equals to null. So previous to inserted of next is also equals to null, and once that is actually done, it will always remain null. So this also becomes null. So let's remove that. So we'll set previous to inserted to be equals to null as well. I think this should work. So let's test it out against 31830. 3183023. Compile and run. Your output is 18 and only 18 is coming in. That's interesting. Previous to inserted of next, that is 18's previous to inserted will be what will be inserting? 30, 18. 18's next. 18's next. No. That's not true. 30 is getting inserted, right? So 30 remains in the place, and 30's next should be null. So 30, if headref of data, so where are we going? This is not true. This will go here. If current not equals to inserted element, so current is equals to inserted element, so we execute this. Else previous to inserted equals to null, and inserted current of next equals to null. Current of next is also, will set this to null. We'll set this to null, I believe. Current of next is equals to null. It is equals to inserted, so yeah, it's the last element, so we'll set that to null. And let's see if this works. 18, 23, 30. I think that should be it. Okay, it's not passing it. What else can we do? We can do this a bit differently then. What we can do is we can maintain a different we can definitely maintain a different list that is that will contain only the, although it's not a different list, we'll just move the nodes from here to there, something like that. So I was trying to do it in place, but I think that will be a bit difficult here. So let's just let's not do it in place right now. What we can do is we can maintain another node star. Let's call it what can we call this? Sorted list or sorted head. Sorted list, sorted head, let's call it, right? Sorted head, and this will maintain the sorted list. And now we have the current list as well, so we'll go through one all the elements one by one. So first element will definitely be there, so sorted head, uh, sorted head, yes, and sorted head equals to headref, and our headref will basically contain the insertion element. So headref equals to headref, and sorted headref equals to headref next. Let's do that as well. Headref equals to headref next, and sorted head of next is equals to null. Sorted head of next is equals to null. Okay, so we have headref, we have done this. So if headref equals to null, headref equals to, or we can run a loop now while headref not equals to null. So while headref not equals to null, and we can return headref here. So we can return headref here. So while headref not equals to null, we'll find the insertion point for headref, right? So we'll find the insertion point. So we'll start off at current equals to sorted head, while, and also we'll need the previous element as well, I believe. So star previous. So first of all, we'll just check here. So if current of data is greater than headref of data. So headref of data, if the current of data is greater than headref of data, that is it is coming to the first place, or equals to, greater than equals to headref of data. So this should come at the first place. So yeah, this should come at the first place. So what we can do is sorted head of okay, headref of next. So here we'll also maintain the next node, so that we can go to it later. So struct node star next equals to headref of next, and here we'll go to yeah, while inside here we'll go to headref equals to next, right? So headref equals to next, and struct node star sorted head, yes. So struct node star current equals to sorted head, next equals to headref next, current data equals to headref is greater than equal to that. In that case, what we'll do is headref of next equals to sorted head, and headref of next equals to sorted head, and sorted head equals to headref, right? And headref equals to next, it will move to that. Else, if that's not the case, then node star is there. Struct node star will also need struct node star previous equals to sorted head, sorted head, yes, sorted head, and current equals to sorted head of next. So while current not equals to null, and current is not equals to null, and current of data, it is also less than will not insert here. So it is also less than headref of data. So headref of data. So while it is less than that, what we'll do is current equals to what? Current equals to, let's increase the screen size. So current equals to yes, current equals to current next. Sorry, and previous will be equals to current first. Previous equals to current, and current equals to current next. Finally, when we are at this, so previous of next, it is less than, right? So we should go ahead. If it is greater than equal to, so that's the insertion point. So previous of next equals to headref, and headref of next head ref of next is equals to current, and that should do. So head ref and return, we should return sorted head. So we should return sorted head. So let's check this out. If this is working, we can test against our custom input as well. 18, 20, 30. So let's submit. I hope this works. Yes, it's working. So yeah, it's always better to keep we can keep another head that will maintain the sorted list. But again, like if we were to do in place, it was actually becoming troublesome, so it is easier to do like this. But again, we can also do it in place as well. I don't think there should be any problem. I think we just messed up on the conditions that we had written, so that's why it became a bit heavy. But again, like this became more logical once we actually split it into this. The time complexity of insertion sort is same. I think everyone knows this. The time complexity for insertion sort will be n squared. The space complexity will be order of one. Order of additional space will be order of one, because if you see, we are not actually creating anything, any array or any list. We are not copying. We are just moving our nodes from one place to another, right? So we are just moving our nodes. So this is how we can solve this question, and I had taken a few tries, which is not expected anyways. But yeah, like that's how we should think. I haven't solved this problem before, so this is the first time I'm solving. And that's how actually you should solve a question in linked list. You should think about how should you move in the entire list, how should you actually move, and how should you make null, like what will be, like how should you move a node from one place to another and everything like that, right? So that's how we should proceed with any linked list problem. So yes, that's about how to solve this. I hope that it's clear with everyone. So yeah, we'll end the stream here, and thank you for joining.